I wanted to start by showing you how to find the critical values of the correlation coefficient. You have to use a different table, so we aren't using the t-table anymore. We go to the column where it says 0.05, and notice how when you're doing a hypothesis test of the correlation coefficient, the df is now n minus 2 instead of n minus 1. In the one sample t-test, it was n minus 1, but now it's n minus 2. So if I told you that the sample size was 20, then the df would be 20 minus 2, and it would be 18. So we would use the 18th row, and then we would go to the 0.05 column, which is the second column over, and it would be 0.444. So for a sample size of 20, the positive critical value would be 0.444, and then the negative critical value would just be negative 0.444. And if I gave you a table, you could just plug those in. If I gave you a table of possible outcomes, and I told you to label where the critical values are, you could just label them at 0.444 and negative 0.444. Or if I just asked you what the critical values are, you could just tell me that they're 0.444 and negative 0.444. So I also wanted to talk about the two-sample t-test, which is the third type of test that we covered. It's meant to test whether two separate populations have equal means, or if there's a difference between the means of the two populations. For example, you might want to test if the mean hours slept by the non-working college student population is equal to the mean hours slept by the working college student population. In order to do this test, you have to sample both populations. So if I'm interested in whether there's a difference in the mean sleep time of working students and the mean sleep time of non-working students, I would have to recruit a certain number of people from each of those two populations. So maybe I would recruit 100 non-working students and 100 working students, for example. And I would collect data from both samples. In a two-sample t-test, the null hypothesis says that the population means are equal. In other words, in my example, it would say that the mean hours slept per night by the 11 million people in the working college student population is equal to the mean hours slept per night by the 8 million people in the non-working student population. So it's important to remember that the null hypothesis of the two-sample t-test says that the population means are equal. It doesn't say that the sample means are equal. It says that the means of the populations that the samples come from are equal. The alternative hypothesis says that the two population means are not equal. So in my example, it would say that the mean of the 11 million people is not equal to the mean of the 8 million people. This just says that you need to, in a one sample t-test, you're supposed to recruit your sample from a population that has a normal distribution or have at least 30 people in your sample. In a two sample t-test, that rule is extended to two samples, so you need either to recruit your samples from two normal populations, or you need to have sample sizes of at least 30 people. In other words, you're sampling from population 1 and population 2. Either population 1 and population 2 have to both be normal, or if they're not normal, you have to take a sample of at least 30 people from population 1 and a sample of at least 30 people from population 2. So it's the same rule, just extended to two populations. In a two-sample t-test, you calculate this t-score, which has a lot of different values from your two samples. It's the mean of sample 1 minus the mean of sample 2 over this square root, which includes the two sample standard deviations and the two sample sizes inside of it. So here's some possible outcomes that might be found. Let's say we're taking a sample of 4 people from population 1 and a sample of 4 people from population 2, and we're recording the hours slept per night by each person. So I'm recording the hours slept per night by 4 non-working college students and 4 working college students. So let's say sample 1 is non-working and sample 2 is working. What this says is that the average of the 4 non-working students is 2.5. In other words, the mean is 2.5, and the mean of the 4 working college students is 7.75. Over here, this is a different possible outcome in which the 4 non-working students have a mean of 6 hours of sleep, and the 4 working students have a mean of 5 hours of sleep. And right here we have an outcome in which the mean of sample 1 is equal to the mean of sample 2. They're both 5. This outcome in the middle shows no evidence against the null hypothesis, meaning this is perfectly consistent with the idea that the population means are equal and that the null hypothesis is true. It doesn't give us any reason to think otherwise. So since there's no evidence against the null hypothesis, it has a t-score of 0. Once you move further in this direction, or as you move in this direction, the mean of sample 1 is starting to become further above the mean. The mean of sample 1 is starting to become further above the mean of sample 2. So here they're equal. Here the mean of sample 1 is 1 above the mean of sample 2. And here the mean of sample 1 is 5 above the mean of sample 2. As the mean of sample 1 starts to become further above the mean of sample 2, going in this direction, the data is starting to suggest that the mean of population 1 is higher than the mean of population 2. In other words, as the mean of the non-working sample starts to become further above the mean of the working sample, it's starting to suggest that the non-working population is getting more sleep than the working population. As we go in this direction, the mean of sample 1 is starting to become further below the mean of sample 2. So here, the mean of sample 1 is 2 below the mean of sample 2. Here the mean of sample 1 is 5 below the mean of sample 2. As the mean of sample 1 starts to become lower and lower compared to the mean of sample 2 in this direction, it's starting to suggest that the mean of population 1 might be lower than the mean of population 2. In other words, as we go in this direction, and the non-working sample is getting further and further below the working sample, it's starting to suggest that maybe non-working college students are getting less sleep, and maybe working college students are getting more sleep, because remember, sample 1 comes from the non-working population, and sample 2 comes from the working population. So if the mean of sample 1 from the non-working population comes out to 2.5, and the mean of sample 2 from the working population comes out to 7.75, that's starting to suggest that maybe the population that this sample came from is getting less sleep, and the population that this sample came from is getting more sleep. So maybe not only is the mean of sample 1 lower than the mean of sample 2, but maybe the mean of population 1 is lower than the mean of population 2. So as we move in this direction, the mean of sample 1 is getting further below the mean of sample 2, and it's starting to show more evidence that the mean of population 1 is lower than the mean of population 2. That's going in this direction. Going in this direction, the mean of sample 1 is getting higher compared to the mean of sample 2, and it's starting to show more evidence that the mean of population 1 is higher than the mean of population 2. So in the middle, we have no evidence at all for a difference between population means. In this direction, the further we go in this direction, the more evidence we have that the mean of population 1 is lower. The further we go in this direction, the more evidence we have that the mean of population 1 is higher. And notice how when we move in this direction, the t-scores are getting further below 0. So when the mean of sample 1 gets further and further below the mean of sample 2, the t-score becomes more negative. And as the mean of sample 1 gets further and further above the mean of sample 2 in this direction, the t-score becomes more positive. Now, outcomes near the center that have a t-score near 0 are pretty consistent with the null hypothesis. For example, if sample 1 was 5.2 and sample 2 was 5.1, 5.2 and 5.1 is a pretty small difference between sample means. So that doesn't provide very strong evidence that these two populations up here are getting different amounts of sleep. So in order to conclude that the populations that the samples come from are getting different amounts of sleep, you have to have a big enough difference between your sample means. Otherwise, the null hypothesis of equal population means will get the benefit of the doubt. If the difference between the sample means is too small, like 5.2 and 5.1, the null hypothesis that the population means are equal up here will get the benefit of the doubt. So at a certain point down here, we're going to have a negative critical value, and up here we'll have a positive critical value. If your outcome is equal to or to the left of the negative critical value, meaning in the negative rejection region, you can conclude that not only is the mean of sample 1 lower than the mean of sample 2, but the mean of population 1 appears to be lower than the mean of population 2. Meaning the result can be, you can make a conclusion where you extend what you see with your samples to the populations that the samples come from. If your outcome ends up at the positive critical value or to the right, meaning in the positive rejection region, you can conclude that not only is the mean of sample 1 higher than the mean of sample 2, but the mean of population 1 also appears to be higher than the mean of population 2. But if you don't reach either critical value, you give the null hypothesis the benefit of the doubt, which means you give the benefit of the doubt to the idea that the population means are equal and that there's no difference between the population means. And I wanted to talk a little bit about what makes the t-score larger in this type of test, meaning what makes it further from zero. You can see how when the sample means get further apart, the t-score gets larger, but the t-score is also affected by the standard deviations and the sample sizes. When the standard deviations of the two samples are smaller, the t-score increases, and when the sample sizes are larger, the t-score also increases. There's only one thing you have to remember about that. But there's only one catch. If the sample means are equal, like they are here, the t-score will always be 0, no matter what the standard deviations and the sample sizes are. Because if the top of the fraction is 0, t will have to be 0. But if there's at least some difference between the sample means, like there is here, then the t-score will increase if the standard deviations are smaller and if the sample sizes are larger. And obviously we don't have any control over what the sample means and what the standard deviations come out to, because this just depends on the data that you end up collecting. What the researcher can control are the sample sizes. So if your t-score comes out too low to reach the critical value, one option is to increase your sample size, which will help you to reach the critical value